So the first lecture, the first hour of this morning's two lectures will be a panorama of everything I want to talk about. So this will be, I will go fast, just showing pictures, some formulas. I will not explain things in detail. And then after that, we will enter in each part of what is contained in the first hour, and we will go in the details. But now I want to go through a quick panorama. So the general framework that I'm talking about is the gravity of binary systems and the motion and radiation of binary black holes. And as you know, this is linked to the beautiful discovery in 2015 of the first gravitational wave signals, initially by the two LIGO detectors. And these events of September 2, the first event was interpreted in terms of the last orbits and coalescence of two black holes a billion light years away. And from the data, one could extract the value of the masses and the spin. And I want to explain that you needed a lot of theory, to go from the data. Why? Because these are the raw data. And if you look at the raw data, for instance, this is the original signal from the first thing, and this is a later signal. So when you look at that, you could think, ah, yes, I see a gravitational wave, I see something oscillating, but you have to look at the scale. The scale here of the variation, this is the raw fractional change in the length of the interferometers. Okay, the detectors we are talking about are laser interferometers. The LIGO ones have arms of 4 kilometers long. And what is represented here is the dimensionless fractional change of the length of the interferometers, delta L over L, which in principle measures the gravitational wave, as we'll see. So if this were a gravitational wave, it would be an amplitude of 10 minus 18, okay? But actually, the gravitational wave here has an amplitude of 10 minus 21. So what you see has nothing to do with gravitational wave, it is red noise. And you have a factor 1,000, so the gravitational wave signal is totally lost in the noise. And so it's the first point. How do you extract? You cannot see the signal really like that. How do you extract it? You extract it by various methods. Like there are fast methods, but which have a low signal to noise ratio, but still they indicate, using, by the way, using ideas of Ken Wilson, because there is a very nice idea of Ken Wilson, which was contradicting a theorem of Balian and Lowe, not contradicting in the sense that there was a subtlety in this theorem. And then Yves Meyer invented an important wavelet, and then Dobelchi-Jaffar-Journet showed how to. So it's just, there is mathematics and there, but I will discuss about what has allowed to measure really the parameters. Okay, we are talking about these signals lost in the noise, and you want to say what are the masses, what is the source, masses, spins. To do that, the method which is used is match filtering, which means you have the output of the detector, which is very noisy. Then you do a correlation with inverse weight by the noise of the detector by a theoretical estimate of the expected signal. This is called the template. So this is this. We are going to describe the theoretical tools that allow to compute the gravitational wave signal emitted during the last orbit and the merger of two black holes, this signal. So you put this signal in Fourier transform here, and then you do for varying values of the masses and spins, and then you look if there are values of the masses and spin that give a good correlation. Okay.
So there is no way to see a signal you were not expecting?
Indeed, except that this type of methods, which are time frequency transforms, they can show in principle that there is something that you don't expect. And actually, in the data, for years, I think now they have understood. They have strange signals that they don't know. I mean, they have things that they think is linked to electric wires and things, or very complicated physics. Okay, so if the signal to, it's a question of signal to noise ratio. If the signal to noise ratio is large enough, you can see a signal that you don't know a priori. Okay, but for the signals like the merger of two black holes, where the signal to noise is not large, you need to know the signal in advance in order to extract it. Okay. So coming back to, just for you to know, you know, the basic things in the history of gravitational waves. Joe Weber is the pioneer of gravitational waves. At a time where most physicists did not believe in the existence of gravitational waves, he said, let me construct a detector. He understood that these were real things, that you could detect them. He constructed detectors. And then after the original mechanical detectors, people developed, starting with two Russian people, Gerstenstein and Pustovoit, the idea of using an interferometer to measure more precisely, to detect gravitational waves. Then many people contributed all over the world. I don't discuss the history of the gravitational wave detectors. Mathematically or physically, what are we talking about? We are talking about solving Einstein's equations. So these are Einstein's equations. The Ricci tensor, I will describe them more precisely. We are going to talk, so there is a space-time of dimension 4 with signature minus plus 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 and pseudo-Riemannian metric. This is the explicit form of Einstein's equation. So here I have chosen a particular coordinate system, okay, just for you to see. These are Einstein equations. These are 10 partial differential equations for 10 variables, the metric of space-time. And they are nonlinear in the sense that the coefficient of the second derivative is the unknown itself, inverse, and there are quadratic terms, products of first derivative and then inverse of this. So it's both, it's more complicated than Young-Mills, but not so much more complicated than Young-Mills. We want to solve this for two black holes, as we are going to see. Black holes have no matter, so in Einstein equation, this is the matter content. If you have no matter, you solve actually Ricci equals 0, so you solve this equals 0, and then you want to solve, it's a pure mathematical problem, two black holes going around, this is a space-time diagram, emitting gravitational waves, coalescing at some point. You want to show how you compute the gravitational waves emitted at infinity by these two black holes from just these equations. Just continuing the basic pedagogy, in case you have not heard of this, what are gravitational waves? At the most elementary level, although this is already a deep level, Einstein, a few months after the discovery of Einstein's equations, and with some mistakes, so he corrected these mistakes in 1918, discussed the simplest gravitational waves, which is saying the following. Einstein's equations are solved by the flat Minkowski spacetime. Now you look at small fluctuations around the Minkowski spacetime. So Minkowski plus a small perturbation. You put this in Einstein equation and you ask what are the solutions of weak perturbations propagating in flat Minkowski spacetime. And Einstein found that the most general solution contains two independent functions. If it propagates in, let's say, the certain direction z, so there are like two independent like electromagnetism, two independent polarization. They are transverse to the direction of propagation, but they are not vector-like. They are tensor-like, and they are described by these two. And the physical effect of gravitational waves on a ring of particles is in the plane transverse to the propagation to deform a ring into an ellipse, you know, this way, and the other polarization does this. He also computed the generation, to lowest order, the generation of gravitational waves by a material source. So now you use Einstein equation with the right-hand side, and he showed that to lowest approximation, the gravitational wave described by this part of the fluctuation of the spatial metric goes with the velocity of light. It's generated by the sort. It goes in all directions at the velocity of light. It decreases like 1 over the distance, okay, you expect, and it is proportional to a certain algebraic projection of the second derivative of the quadrupole moment of the system. And then from this, he also said, okay, now I know that, so it's a quadrupolar wave emitted by a general moving masses. He also computed the loss of energy. He said, okay, let me compute the energy momentum tensor of the gravitational field and compute the flux of energy and angular momentum from this, and therefore predicted that moving systems should lose energy and angular momentum to gravitational waves at infinity. Now, I want also to pay homage to somebody who is well known here in Saclay, a friend of all of us, Freeman Dyson, because Freeman is one of the pioneers of the idea of that, the following idea. If you take Landau-Lifshitz, in Landau-Lifshitz, this is what Freeman did, there is an exercise about gravitational waves where he improves the derivation of Einstein, and he says, let's compute the loss of energy by a binary system. And this exercise explicitly pushes you to conclude that this is so small, and it is written in Landau-Lifshitz first, that it has no physical effect. That the loss of energy by two stars moving around is so small that you can forget about it. But what Freeman did was to solve the exercise completely. So what is the exercise? You write that you have a binary system with this energy, sum of kinetic energy and binding energy on a circular orbit. You assume that there is a balance between the loss of mechanical energy of the system and energy lost to gravitational wave at infinity. So you write that the time derivative of this is minus the flux of gravitational wave at infinity. You use the Einstein quadrupole formula to compute the flux with 32 over 5 and then this, and you solve this equation. And indeed, if you solve it at time t and the two objects are far separated, the change of the orbit is totally negligible, it's very small. But anybody of you, if you look at this equation, you should be able to solve it instantaneously. And then you find that the solution is that the distance between the two bodies will slowly decrease, but it decrease, and at the end it gets so small that you emit more and more gravitational waves. So you end up with a catastrophe where you emit, first you end up with the coalescence of the two things, and at the end you emit an intense flash of gravitational wave. And that's what he said in his paper, saying the most interesting thing is to put two compact objects like two neutron stars, and during their last orbits, they will send a signal of unimaginable intensity. And he said one should have detectors of the type of Weber's type to measure it, okay? So he had the vision, but this vision says that the most interesting signal is what happens at the end. And at the end, you cannot use here, one was using the lowest order formulas like Newtonian energy, lowest order quadrupole flux. In order to face the computation of the end of the signal, you need to refine this. And this is what I'm going to talk about. All the elements that are needed to, which are detailed here. The basic physical mathematical tools which have allowed one now to predict, I showed before a signal of the coalescence of two black holes. This was predicted before detection and before numerical relativity, actually by analytical methods, and this is what I want to explain. And this used several physical mathematical methods that the aim of these lectures is to explain them conceptually. There is the matched asymptotic expansion approach to the motion of black holes and strongly self-gravitating bodies. There are several approximation methods because Einstein equation you cannot solve analytically like that, so you need some type of perturbation theory. There are several types of perturbation theory that will play an important role. Perturbation theory post-Minkowskian, which does not assume that the motions are small compared to the velocity of light. Another one called post-Newtonian, where you use the fact that v over c is small, that the velocities are small compared to the velocity of light. A method to compute the emission of gravitational radiation by a binary system. a method to resum everything and to be able to describe the last orbits, because beyond perturbation theory. Then I will briefly mention that mathematical aspects were important, not for this thing, but for the numerical relativity, which was important to check and get better information about non-perturbative aspects. Okay? Now, let me start this panorama by saying, so now I talk about what are the methods to describe the motion of two bodies, of binary systems in general relativity, okay? Because Einstein's equations say that matter is creating a curved space-time. But then how, from this beautiful idea, you go back to the idea that there is a gravitational force, that bodies go around each other? How do you do? Initially, Einstein started the discovery of general relativity by saying that if I have a test particle in an external gravitational field, so it's point zero, then it should follow a geodesic. That is, it should follow the elements, the lines of smallest or largest distance time, proper time. Then he introduced approximation method, because this is for a test particle in a gravitational field. So you need to compute the gravitational field. So let me re-explain, I mean, just give you the language. The post-Minkowskian approximation method consists in saying you look for solution of Einstein equation where the metric G mu nu is the Minkowski, the Poincaré Minkowski metric, yeah, I should say here, Poincaré Minkowski, eta mu nu, plus H mu nu, a perturbation which is supposed to be small, and the only thing you assume is that H mu nu is small, and then you do a perturbation theory in the strength of the perturbation. In the post-Newtonian approximation method, which was introduced very early, you, I should not touch, you also use the fact that you have another small parameter, not only the gravitational field, which might be small, linked to G, the Newton's constant, but V over C. If the source of the gravitational field is moving slowly, you can use this twice. You can use it in the sense that there are terms in Einstein equation that are proportional algebraically to V over C, so you have a small parameter in the source, but also the fact that if two bodies move slowly, the propagation of gravity at the velocity of light will be very fast compared to the motion, so you can neglect probably in the near zone the time derivative, which is actually 1 over c d by dt compared to the space derivative. So you use that. This was used initially to describe, to solve Einstein equation, and now to solve the motion of weakly self-gravitating extended bodies like the planets. I mean, initially people said, how do I explain now in general relativity the motion of the Earth and all the planets in the solar system? I need to do that. This was done by using this perturbation theory, and then writing that each body, that the stress energy tensor of the matter is conserved. As you know, I will remind you, Einstein equations are such that the left-hand side is automatically conserved, and this implies that T mu nu, the stress energy tensor, satisfies this conservation law. And then you use this, which expresses the local equation of motion from the body. You integrate over the body, and then you try to derive equations of motion for planets. But in the following, we are not interested in the motion of planets. We are interested in the motion of black holes. What are black holes? Black holes were actually first found by Schwarzschild a month after Einstein found these equations. And by the way, as you know, a fantastic thing is that Schwarzschild means black shield. So the guy who invented black holes was called Black-Shield. And he found this first solution. So it's an exact solution of Einstein's equation. And at the time, he was looking for a solution of Einstein equation spherically symmetric corresponding to a point mass. He was looking and saying, let me look for the exact solution of Einstein equation for a point mass. And that will be important in the following. But what was surprising is this thing, you know, something happened in this solution when the radius, the distance from the center, is equal to 2gm over c squared. This is infinite and this is 0. So for 50 years, people were mystified. What do we do with this 0 infinity in this thing? It took a very long time, because it was a subtle conceptual thing. So many people, Oppenheimer actually was the one who really introduced the notion of black hole in 1939. And the modern view is that when a star collapses, it deforms the structure of space-time, and there exists this hypersurface called the horizon, the surface of the black hole, which is where this is 0, where r equal. But this hypersurface is a regular hypersurface in space-time, which separates a region of space-time out of which light cannot escape. It is tangent to the light cone, which means light emitted from inside this region of space-time does not go outside. Anyway, what this shows is that a black hole is a complicated object which is strongly self-gravitating. I mean, it's the most strongly self-gravitating object. So the immediate question is, how do you describe the motion of black holes? You know, black holes are not planets where you can use a weak field approximation method. So you need something else. And this thing that I will explain in detail consists in using matched asymptotic expansion methods. So you want to treat the motion of two objects like that, or two neutron stars, which are also strongly self. So we will need a special method by combining approximation methods to treat the motion of two black holes. But technically, you need to do calculations at high order of perturbation theory, and then you realize that the general conceptual method of matched asymptotic expansion actually is, although it gives the answer, is complicated to use. So you do a formal trick which consists in replacing the extended objects you talk about, neutron stars or black hole, by point masses. So now this should not be allowed. That is to say, a neutron star is not a point mass, a black hole is not, and there is nothing inside the black hole, so you cannot say there is a point and a delta function. But let's do it. And when you do it, you have immediately the problem that you are putting delta functions, point mass, in a nonlinear theory. So although this is a classical theory, you have self-gravity effects. Like, for instance, this diagram means I have a point mass here, which creates a gravitational field, and I need to compute the value of the gravitational field at the point where the point mass is located, and this is evidently infinite. So you need techniques borrowed from quantum field theory of initially analytic regularization, and as we will discuss, dim-reg, dimensional regularization, actually was essential to do the calculations because it is better. And we will explain why this thing, so long ago I had proven that this formal thing actually gives the good answer. You have to prove that it's not just a formal regularization, but using regularization in a certain way gives the correct answer for two black holes. Now let me tell you about what was explicitly done for explicit calculations of the motion of bodies in general relativity. At the end of 1979, Joe Taylor announced that he had measured for the first time that in a binary pulsar, the orbital period of the system was decreasing. And from the argument of Landau, Lifshitz, and Dyson, if you want, this could be heuristically linked to the fact that if the system of two neutron stars is emitting gravitational waves at infinity, there is the loss of energy at infinity, you should pay this energy, so they have to get closer, and therefore the orbital period has to be faster, shorter. But this was a heuristic thing. So everybody said at the time, but can we prove this really, that in Einstein's equation, two objects will get closer and the orbital period will change? And at the time, people were aware that if you try to prove it by using post-Newtonian approximation method, this is not conceptually very good because the post-Newtonian approximation method was assuming that the time derivatives are small compared to the space derivative, which means that instead of having propagation at the velocity of light, a D'Alembert equation, you put a Laplace Poisson equation. So this is valid in the near zone, but not in the wave zone of the system. So it was not a good starting point. That's why, at the time, several people embarked on a program of solving the two-body problem without using a post-Newtonian approximation, but only the post-Minkowskian. That is, you use perturbation theory. You solve Einstein equations like that by successive powers in H. but without ever assuming that the velocities are small. This allowed us to compute explicitly the equations of motion. So you see it starts being complicated. You compute, we will describe this in detail. You compute the acceleration of one world line influenced by the gravitational field created by the other world line as a succession of terms in an expansion, including terms like that evidently you would call one loop in QFT language. But classically, this one loop means, you know, that this body creates gravity, and let's take this diagram. The first body creates some gravitational field. The second body creates a gravitational field. These two gravitational fields act non-linearly on itself because there is energy in the gravitational field, and that recreates a secondary gravitational field. So this is the cubic vertex of Einstein equation, terms cubically nonlinear in Einstein equation, which acts back on the first body. So all these one-loop diagrams are just classical things, which means you have nonlinear effects in Einstein's theory. And then we went to some two-loop terms also. Anyway, at the end of all this method indeed gave the equations of motion of two neutron stars up to a level where, with Natalie, we could compute the orbital period change, and this was in agreement with the observation of the binary pulsar. Okay. This was, so the post-Minkowskian method was used in order to avoid having a method which is only valid in the near zone, okay? Because it's make no near zone assumptions. But the problem is that it is difficult. It's actually, this method leads to complicated integrals. We will come back to this. And to go beyond, in order to solve Einstein equation to higher accuracy, at the time it was convenient to say, okay, let's forget about mathematical rigor, and now let's try to go beyond the level where things were computed, which was V over C to the 5th power, and use the post-Newtonian approximation methods, although it has defects, but it's more efficient, as I will describe. But for this, we are going to go back to the heuristic point of view. We will solve two problems separately. We will solve the problem of the conservative dynamics of the two bodies, how the two bodies interact under a potential which will be like a Newtonian potential with corrections, something which is an Hamiltonian description of the two bodies, neglecting the effect of the emission of gravitational waves, so neglecting radiation damping, or taking the conservative part of the dynamics, and then separately compute the emission of gravitational waves at infinity and take this emission as a back reaction on the motion of the system. You separate the problem in two parts, and this way you can solve each problem to higher accuracy. How do you solve, now I discuss quickly, how you solve the problem of the Hamiltonian, the conservative dynamics of two bodies. So if I were Newton, that would be, you know, just I have two bodies, I have the kinetic terms, and I have the -1 gm1 m2 over 1 over r interaction, okay? But you want to do that to much higher accuracy. The way you do it is to compute the reduced action, okay? The reduced action means the following. We are talking about the classical theory of the interaction of two point masses interacting by a field, g mu nu, gravitational field. So the original action has like the geodesic action that I've shown before, point mass action for particles moving in the g mu nu. You have for two particles. You have the Einstein-Hilbert kinetic term of gravity, the action describing gravity. You need to add a gauge fixing term because if you solve, you know, Einstein equations without fixing the coordinate condition, you cannot solve them. They are not hyperbolic, they are not elliptic. You cannot solve. The propagator is degenerate. Okay, you cannot invert it, so you need to put a gauge fixing. And then this is an action for the motion both of the field, so it's an action for the coupled system of the field and the particles. What you do is you integrate out the field, which, by the way, may be surprising from the QFT point of view in the sense that when you integrate out a field, usually you integrate out a massive field, which has you can integrate out the electron field from QED, for instance, to get an effective action for the photons, okay? Here you do the reverse. You say, let me integrate out the gravitational interaction to get an action for the two world lines. This was first introduced by Fokker in the case of electromagnetism. So this way, the way you do it is you need to solve the field as a functional of the two world lines, and then you replace this in the action, and then you get an action for the two world lines. And as we had shown long ago with Esposito files, this can be expressed in terms of diagrams, which are the following. So technically, it's this. The metric is this plus this. You have the action which contain H and the matter. You solve for H in terms of the matter, and then you get a reduced action for the interaction of the two world lines. And then at lowest order, you get like the one graviton exchange. So this is the interaction of two world lines by the exchanger. And then you get higher things. This was computed to 4 loops. Okay. So using the post-Newtonian method. Actually, this computation would be extremely difficult for loops if I was using the post-Minkowskian thing. But using the post-Newtonian allows to compute 4-loop things. I will explain why these very complicated things were doable. But when you do these computations, you really have still complicated integrals. You have UV divergences. And we will have to discuss why dimensional regularization was useful in this framework. Let me just describe quickly the results. So so here I'm summarizing what is the computation of the Hamiltonian of two interacting point masses going around. At the first correction beyond Newton, evidently, the first solution was obtained by Newton before Einstein. But then the first correction in V square over C square was computed actually by Lorenz Drost, but it was forgotten, and Einstein in field of Pide in 1937. The second correction in V4 over C4 was first computed actually in 1982. And then the first then it was computed to V6 over C6, and recently V8 over C8. This is the first computation. So all these things, let me just flash this. So the Hamiltonian looks like that. At the Newtonian level, you recognize Newton, P squared over 2m, the kinetic term, minus the Newtonian interaction. At the next order, you have corrections in P4 over, m1 cube, and then you have corrections to the gravitational interaction. This is at the next level here. This is the next level, and this is the for-loop level, okay? So we'll see that these results are necessary. They say you want to use perturbation theory to increase the accuracy of the thing, but at the same time, they are not sufficient because the perturbation theory breaks down at the moment where you most need it, which is the coalescence of the two black holes. So you need to do that, but you need to go beyond perturbation theory. But here I was describing the conservative dynamics. What was done separately was a perturbation theory to compute the emission of gravitational waves by a binary system. So the method which has been used, actually the best method, is the multipolar post-Minkowskian method we introduced at the end of the 80s. And let me just describe the final type of results. It allows you to improve the quadrupole formula of Einstein much beyond its scope. The gravitational wave at infinity is written finally as an integral which itself contains nonlinear effects over the source, and then there are tail effects. That is to say, there are many. The wave emitted at retarded time t minus r is not linked to the state of the source at the retarded time, but contain integrals over the past. You have many nonlinear effects, which means you need to integrate over the history of the system also. So so at the end, you compute the flux, for instance, here. This is the explicit present calculation done by this method of the flux emitted by a binary system, okay? The first term here, corresponding to this one, is the Einstein quadrupole formula with 32 over 5 that I already quoted. And then this is a v square over c square correction, a v cube over c cube, a v4 over c4, up to v7 over c7. So you get corrections to this. But again, this is absolutely necessary, but not sufficient, because near coalescence, actually each term in this expansion is comparable to the previous one, because this is where something happens, you know. So you want to have this, but you want to do something more. This led to a debate because at the end of the 90s, our American colleagues, they had recognized that indeed these perturbative expansions were breaking down at the moment where you most needed them. So they said, we can use perturbation theory when the two black holes are far apart, but during the last orbits, we cannot use this. It's slowly convergent, it's bad. So we will need numerical relativity. Let's wait until numerical relativity works. If we don't have numerical relativity, we cannot do anything. We cannot compute what is the merger of two black holes. In Europe, we were more bold, and we said, no, let's invent a new method which will allow to compute the last orbits and the merger and the post-merger. And this is what we did with Alessandra Bonanno. We computed the first complete signal by using a resummation of perturbative results. So the main thrust of the lectures will be to explain actually what is this method. So here I'm just saying that its name is effective one-body. Is it on the next thing? Yes. Effective one-body method, which incorporated several things. I want to say that actually this method, because here in Saclay, was triggered because during one weekend, for mental rest and intellectual amusement, I was rereading Itchikson-Zuber, the quantum field theory book. And in it, there was an interesting paragraph about two-body effects in interacting QED interacting systems, both I think the positronium and the hydrogen atom. And they were saying, alluding, without giving references, to a paper actually of Brezin, Itchikson, Zin-Justin. And actually I went back to Itchikson-Zuber to check that, and this thing is clearly said only in the French edition that I had, which was a Saclay preprint of the time. In the English edition, it is less clear what they are talking about. But anyway, reading this said, what they were saying is there may be a way to treat a two-body problem as if it were one body in an external field or something like that, replacing two body by one body. And then the idea was, let's see if we can do that in gravity. So technically, one could not use what they were saying like that, but saying, can we do that? And this was the idea of this effective one body that we developed with Alessandra Bonanno. So the idea is, we have really the interaction of two black holes, a two-body system. Does there exist an equivalent description, which is not a two-body system, but which is a test particle, really a test particle, moving in an external gravitational field that you don't know, an effective gravitational field, G mu nu effective, such that the geodesic motion of this particle in this effective metric is equivalent to the very complicated dynamics of the two-body system, okay? It's not at all evident that you can do that, and but actually you can. I will describe how the way to set up a dictionary, because now I'm saying let us prove that a two-body Hamiltonian is equivalent to one particle in an external field. How do you even do a correspondence? What is the energy of the effective particle compared to the real energy of the binary system? What are the position of this? How do you make a dictionary? It's useful to think quantum mechanically. I will describe how thinking quantum mechanically about a very classical system allows to set up a dictionary. And at the end, for instance, here I've written explicitly the explicit effective one-body dynamics of a system of two black holes at the third post-Newtonian approximation, which means V6 over C6. You know, this is the three-loop. So it's a three-loop approximation to Einstein's equation. is equivalent to saying that the effective particle satisfies a mass shell condition, which is a geodesic term plus a correction which is quartic in momenta. The effective metric is spherically symmetric, described by two functions, and these functions are given by very simple formulas. This, you know, these coefficients, so here there are 1, 2, 3, 4, 5 coefficients. This is equivalent to all this thing. So it's a huge compression of information. You have something complicated, and now you have something much simpler. Actually, I was talking up to now about the motion of two non-spinning black holes. I was saying black holes is like a point mass. We know that a black hole can rotate, and therefore you need to endow those two word lines by spins also. The effective one-body method has been extended for the spinning case. It gets more complicated. I will not enter into details. So here I was describing, so what I just said was, so the history of the computing the conservative dynamics of two black holes was compute the Hamiltonian as an expansion, realizing that this perturbative expansion is not good at the moment where you most need it for the last orbit, replacing this conservative dynamics by this effective one-body description. We will see later why this effective one-body description is better to describe the last orbit and has allowed to predict what happened at the merger. But we need also to resum the emission of gravitational waves, because I have shown before that the flux emitted by two bodies is given a priori by a perturbation expansion, which also breaks down. So if you want to add radiation damping to the motion of the conservative system, you need to resum not only the dynamics, but also resum the flux emitted at infinity. This was done by special methods, like for instance, by looking at the formulas, one realized that there are many log terms which are contribute to the bad convergence, and then one could resum an infinite number of log terms, like, you know, resumming leading lobes to all orders by solving a Coulomb wave equation. Okay, so one introduced some methods, then you can introduce their gamma functions, they are, okay, and at the end you simplify this expansion and you rephrase it in a form which is visibly better. So at the end you can also resum the gravitational waves emitted at infinity and the effect of the emitted gravitational waves on the motion of the system. And now I can just, it should work. Yes. At the end, what the effective one-body description is giving a system of ODEs for the motion of the two bodies with a resummed Hamiltonian and a resummed radiation reaction force put here. This allows to compute the motion of the two bodies and at the same time to compute the wave emitted. So here you have the motion of the two bodies. Here at the same moment you have the wave emitted at infinity. And it starts again. And this wave, so the description here I've been describing how to describe the motion of two black holes by 2 point masses. It's a resum description, but these are still 2 point masses. Evidently, at some point, I have to say these two black holes are not point masses, they are two, yeah? And they will, in a sense, coalesce. How do I do that? We invented a way within the effective one-body method to describe at which moment you replace the 2 point masses by what you do looks very coarse, because what is done analytically is to say at some point I replace the two black holes by one final black hole, which will be the coalescence of the two black holes, but which is perturbed and which therefore oscillate, because if you put two black holes, you know, like you can imagine two soap bubbles, when the two soap bubbles touch, they form a bigger soap bubble, which has not the good equilibrium shape, so it will vibrate. And there was the notion of vibrations of black holes, so you can write the signal at the end, after merger, as a sum of vibrational modes of the black hole. So anyway, this is the way. Yes, this is, so in 2000, this method led to the first explicit computation of the full gravitational wave signal. So these are like the last, you know, three orbits here. This is the merger of the two black holes, and this is the final signal which decays very fast. When the two black holes coalesce, they form a black hole which vibrates, and then there are so-called quasi-normal modes, which are damped modes, because when a black hole coalesces, it vibrates, but these modes emit a lot of wave at infinity, so they decay exponentially. So this is the final signal. We also showed how to do it for spinning black holes at the time. 5 years later, so that was 2000, 5 years later, the first numerical computation succeeded in computing the coalescence of numerically of two black holes. I should say that these methods were based on mathematical works. A lot of them were done by the French mathematical school from Damour, Nishnovich, Choquet-Bruat. I mean, a lot of mathematics was used in order to set up the codes. But still, these numerical codes, for 30 years, you know, they crashed. As you say, people for 30 years tried to simulate two black holes. They wrote codes, and you launch the code, and the two black holes cannot even move, that the thing crashes. But finally, a young postdoc student, Franz Pretorius, alone in his corner in Caltech, was the first one to solve the thing. So that was the breakthrough in 2005. Soon after, one could compare, in this work, the numerical signal of the emission of gravitational wave by two black holes to the analytical effective one-body one. And this is the comparison of the evolution of the frequency of the gravitational waves just before merger, during merger, and after merger. And the green curve is the 3.5 PN effective one-body thing, and the black curve is numerical relativity. Actually, here, the difference is due to numerical errors, because EUB actually described very well here. And what you can see from this is that the effective one-body analytical method is close, that is, is capturing, indeed was correct in capturing what happens at the merger of two black holes, but that after merger it's not very accurate. And this led to the idea in the following years, because in the following years numerical relativity could compute many more waveforms, but still each one of these things is the waveform emitted by the coalescence of black holes with mass m1, mass m2, spin s1. I mean, you have many parameters. And each computation takes more than a month. And for the detection by the method of match filter of LIGO-Virgo, you needed 250,000 templates. So evidently, a quick calculation shows that you cannot use numerical relativity to compute 250,000 templates. They were computed by the effective one-body analytical method, but improved by comparison with numerical relativity. Because the idea is you have an analytical method which captures most of the physics, but which is not very accurate during merger. You have numerical relativity, which cannot well describe the perturbative theory for many orbits, but which is good at merger. Let's try to take information from numerical relativity to improve the analytical thing. And this is what was done in the years after. For instance, in this formula, which is one of the coefficients of the metric of the effective one-body description of the interaction of two black holes, everything which is here, 1 minus 2u, actually, u is gm over c square r. So this thing is the Schwarzschild solution. You recognize 1 minus 2m over r. These are analytically computed things at, 2-loop, 3-loop, 4-loop. And here, at the level of 5-loop, the log term is computed, but the non-log term is not computed. It's very complicated 5-loop computer that nobody has adapted yet. And what you do is you say, but there will be a coefficient. I don't know how to compute it. Let me assume some value and compare to numerical relativity to extract a numerical value of something which is a 5-loop thing that I cannot compute. And then you get these numbers, which are now not analytic numbers because they are fitted to numerical relativity. And now you use this instead in the analytical framework. So this is the way in numerical relativity you extract some information, non-perturbative information from the numerical relativity simulation, but you put them in the analytical framework. I will describe later that actually the analytical description was already very close. This is the best numerical relativity fitted value of the A function, and actually it was very close to what was analytically computed. So maybe we were lucky in the sense that we could have been wrong, but we were very close to reality. And this shows also, this is a close-up on the gravitational waveform emitted by two black holes. And here there are two curves. There is a black curve and a red curve. And the red curve is the effective one-body. The black curve is the numerical relativity. And you see they are really on top of each other after tuning some parameters to numerical relativity, except here where you can see a small deviations, okay? Yes, so the 250, yes, so this is, so 250,000 templates were computed, 50,000 of them were post-Newtonian because they did not need the merger, 200,000 of them were the effective one-body, computed by the group of Alessandra Bonanno, who had left in the US at this moment. These were the ones used to filter the noisy detector's outputs. But after detection, you want also to check that the template you used was good. So people redid numerical simulation of two black holes with the value of the masses derived from the template to check that there was nothing missed, you know. And this was done, for instance, for one of the detection, this one. But I want to insist that the numerical simulation done for this thing took 3 months and 70,000 CPU hours. So you see one template, which in reality lasts a few seconds, takes today with the best computers still 70,000 CPU hours, okay? So it shows it's not efficient numerical relativity yet. Let me not spend time on this. This is just to show that contrary to what one believes, if you look at this, even in the first signal, which I said was lost in the noise, most of the signal-to-noise ratio does not come from merger, because it seems that you can see the merger, it's true, but the merger is only a small fraction of the signal-to-noise ratio. Most of the information in this thing is in the inspiral, in the last orbits before merger. Okay. Now, the last part of this panorama is I have described how this effective one-body method was used to compute these templates and how it used several perturbation theory methods, post-Newtonian, post-Minkowskian. It also used numerical relativity. I will describe in other talks how it used also self-force results, black hole perturbation theory. Now, what I want to describe is a new avenue of research, which is the link with quantum scattering amplitudes. Recently, I have emphasized that the effective one-body method can be used as a medium to translate between results from quantum scattering amplitudes and LIGO-type physics. That is, say, you start from a quantum scattering amplitudes under gravitational interaction, and you want to massage it to extract from it information useful for LIGO-type physics via the effective one-body method. So that will be the end. Yes?
Before you go further, could you give a little bit more insight on why this effective one-body method could be such a step forward? Because in other fields, it looks a trivial idea to have an effective field theory in a kind of some kind of effective mean field background. So here,
maybe we will, okay, keep this question. Maybe let me finish this because I want to have a break now. And I want to introduce this. So we will come back to this. First, the idea that already in the 60s and 70s, some people worried, I mean not worried, but they said, to compute the gravitational interaction even of classical bodies, can I use Feynman scattering amplitudes, okay? And some calculations were done, in particular in the Japanese group. For instance, Iwasaki computed really Feynman scattering amplitudes under gravity exchange, you know, at the one loop level, okay? using post-Newtonian also approximations, slow velocity. So he computed this ladder diagram, cross ladder diagram, and then really this one loop and these things. And then he tried, then he recovered from this the Einstein-Infer-Lofman Lagrangian that I have shown before. As you know, for many years, Amati, Ciafalani, Veneziano have considered the ultra-high energy scattering of string modes, but low-mass string modes, which means essentially gravitons. So you take gravitons at ultra-high energy, and you make them collide, and you look at the scattering matrix. And this is the only computation in the literature of a two-loop effect, okay? So they computed the two-loop diagram. These things means Regge-Gribov dressing of many things that I will not describe. They computed from this the eikonal approximation of the scattering amplitude. And the aim of these lectures was to start a dialogue with people in Saclay, and notably John Joseph Carrasco. Bonjour, John. Because now, besides this thing, which is the only existing two-loop calculation based on string theory methods, there are, as you know, many progress in computing gravity amplitudes using on-shell method, using double copy. And the idea of this is to show how you can translate between a quantum scattering amplitude and an effective one-body description, which then gives information for classical gravity. So it's, let me describe, this has already been done, starting from the two-loop computation of Veneziano and collaborators. So using this high energy, by the way, this result is a two-loop result, but only in the ultra-high energy limit, which means you take a limit where many terms disappear, the masses of everything disappear, you have only, ultra-high energy things, so you get some information, but a limited information also. When you do that, I have shown recently that the quantum result of Amati, Ciafaloni, Veneziano is equivalent to an effective one-body description at ultra-high energy, which is given by this metric, which is a conformal metric. It's in a conformal class. And so this function A is the same function A that I showed before, how it was computed analytically, how it was improved by using numerical relativity. But now, so there is the famous 1 minus 2u, which is Schwarzschild. It's 1 minus 2 gm over r. And this term here, which is, so u is gm over r. So something which is u to some power is Newton's constant to some power. So it gives you the order of approximation. So here we had order g square, which is the second post-Minkowskian. But this we had computed classically long ago. So actually, I could check that this coefficient extracted from Amati was the one that we had found before. But these new coefficients have been extracted from the result of Amati and are not computed. This is like a third post-Minkowskian and a fourth post-Minkowskian thing, which is 2 loops and 3 loops, which are not computed. And last slide, if we, I will also describe how the present results I've been able to check that if you take the one loop, okay, this is the one graviton exchange, so it's 2 word lines exchanging one graviton, so no loops, okay. It's in Feynman language, this is a trivial calculation. You just write, the vertex, the way the graviton couples to the 2 word lines, and you divide by 1 over k square, okay, which is gives minus t, the Mandelstam transfer square energy, square momentum. And I will show how the 2 loop effect, the 1 loop effect is, so what was done here was to start from the effective one-body description post-Minkowskian at the 1 loop effect, to quantize it, to compute the quantum scattering amplitude from the effective one-body and compare to 1 loop quantum calculations. the surprising thing was when I tried in the literature to find one loop results, which in principle in any field one loop, are not difficult. Okay, actually the results were not fully correct. They were wrong signs inside the formulas, and the referee said, but there is this recent calculation of Guevara that you should check, and indeed modulo an overall sign which was wrong again. The result of Guevara at least coincided with the classical result quantized this way. Yes, so that was the last transparency. Let's have a break and this panorama, then I will enter in details after 10 minutes of break.
Okay.
Okay, so let me now start the second lecture. We'll start entering into details of what I have sketched as a broad brush description. I will now talk about the motion of a system of 2 or n strongly self-gravitating bodies. So the issue of how you deal with the fact that you cannot use perturbation theory near each object. Okay. First, let me make clear my conventions. So I use the signature mostly plus. You have the metric of space-time. When using coordinate system from the metric, you define the Levi-Civita connection via the Christoffel symbols given by these 3 terms. This is when you use a frame, so we don't need this. From Christoffel symbols, you define the curvature tensor, which is derivative of the connection plus connection times connection. This is a 4-index object, the Riemann-Christoffel curvature tensor. If you contract the Riemann curvature tensor over these indices, you get an object which contains 2 derivatives of the metric, which is the Ricci tensor. The sign conventions are used is that the Ricci tensor and the curvature tensor are positive for spheres, if they are Euclidean spheres. And then the Einstein tensor is Ricci minus 1/2 of R g mu. Einstein equation is that the Einstein tensor is proportional to the stress energy tensor of matter. R is the Einstein-Hilbert action is the space-time integration of the curvature scalar. And several times I will say I use harmonic coordinates. Harmonic coordinates is a way to gauge fix, not completely actually, coordinates in space-time by saying that each coordinate satisfy the Laplace-Beltrami is harmonic, that you say. The Laplace-Beltrami operator, the covariant second derivative under g mu, acting on the coordinate is 0. So this is h lambda by definition. So inexplicitly, it means it's a kind of Lorentz gauge condition. It is a generalization of d mu a mu equals 0. Okay. Now we have seen already this. So we are going to tackle these equations. So again, let me say, historically, the first method to solve the motion of bodies was to say, okay, we are interested in planets. That was evidently in 1916. There were no black holes around or neutron stars. So you said we are interested in the motion of planets or stars. So you want to solve Einstein equations, but a planet, when you put numbers in, is a very small deformation of flat space-time. For instance, the sun is changing the geometry h mu nu by 10 minus 6. The Earth by 10 minus 9. So you have small parameters, and then, okay, you say, I will use perturbation theory, first order, second order, if I need in h mu nu. The planets are moving slowly, so I will use also the fact that the velocities are small and time derivatives are small compared to space derivatives. Then, from Einstein's equation, I did not say that, the left-hand side of Einstein equations, the Einstein tensor, satisfies a so-called contracted Bianchi identity, which is the covariant divergence on the left-hand side is 0. Therefore, it implies that the covariant divergence of the right-hand side is 0, which is the local conservation of energy momentum of matter in presence of a gravitational field. So you can use that to try to get the motion of bodies, because this equation tells you how the field lines, the body elements are moving in space-time with some constraint. So initially, people said, let's solve Einstein equations and then insert that to compute the motion. Let me just give you some details to give you a... So how do you solve Einstein equations now explicitly beyond linearized perturbation, okay? We will need immediately, even at the lowest approximation, we will need some nonlinear terms. How do? You start from these equations, and then you realize that because the source of this equation will be the stress energy tensor, and the stress energy tensor is linked to the fact that you have bodies moving. Like if you put a perfect fluid, you have the four velocity of the fluid, you have the pressure, but you realize that the four velocity is a slow velocity compared to another one. You have slow velocities there, okay? You say you have two bodies. So at the end, you find that the component T00 is much larger than the component T0I and much larger than the Tij. So you use this to say, okay, in the source, I have things which are formally of order c squared, c1, c. You use c, the velocity of light, as a formal perturbation parameter. And then you write Einstein equations. You keep nonlinear terms, but what you do is you keep this term here you keep the D'Alembert part of this term exact. So here I will not assume the approximation that when I have a D'Alembert operator, I neglect the time derivative because it's better not to do that. So this term will give a D'Alembert, but then I have many nonlinear terms. These nonlinear terms, they are really very complicated. You know, the big difficulty of Einstein's gravity is that the cubic vertex is extremely complicated. I mean, it is obtained from all those terms, and there are many index contractions. But if you are in the post-Newtonian approximation, what happens is that you find that one component, G00, is dominant compared to the other one, and the part which has two indices ij is linked to G00. So actually, it simplifies very much. You find, by looking, that there are not so many contractions to take. At the end, you find that Einstein equations can be written this way. And here I have put D'Alembert of the log, which means that I keep the term, it's a nonlinear term. You know, if you differentiate a log, you have a nonlinear term. So all those nonlinear terms here, they have been absorbed in the fact that I could define the log. But what it means is that if I introduce parametrization of the metric, if I say, let me not write that G00, you know, is 1 plus small thing, but that G00 is an exponential of a potential, then this potential will satisfy a very simple equation. D'Alembert of the potential equals something simple. And this is something we had done at the end of the 80s, and also introduced this combination because you find that, so at the end, if you parameterize the metric, you know, with some exponential, you find that it simplifies Einstein's equations. And by the way, this thing that we had discovered long ago has been rediscovered in a different guise as a temporal Kaluza-Klein reduction by Cole and Smolkin 10 years later, or like you, maybe I made a mistake, no, 20 years later. And then let me also mention, so here I'm just saying it's a technical point, that it's useful, you know, just to represent Einstein variables sometimes in a different way, like exponential, because it simplifies the field equation and other things. There is another decomposition which says we are talking about a space-time where time and space should be on the same footing. But actually, we are talking about the evolution of a space-time in time. So it can be convenient to say, let me set up a slicing of space-time by t equal constant hypersurfaces with good choices of this. And this is the 3+1 decomposition of Einstein equations, which has been first written down by Madame Fourès-Breuat, Choquet-Breuat in 1956, and which has been transformed in an Hamiltonian framework by Arnovitt, Deser, and Misner, which will play an important role. So in this description, instead of using, you use this other description of space-time, where you have the metric of the spatial slices, and then you have a function called linked to G00 called the lapse, and a function linked to G0i called the shift. Okay. At the end, what you find is, now I'm showing you the explicit solution of Einstein's equation at the first order beyond linearized theory, where I take into account the leading nonlinear terms, okay, in the post-Newtonian sense. So I have some one-loop effects, some nonlinear terms in Einstein equation. And you find that if you use T mu nu in these combinations, Einstein equations become, that V and Vi satisfy linear equations, because what this is saying is that I have D'Alembert of V equal a certain source, this source, D'Alembert of Vi equal this, so I can solve explicitly. I just need the green function for D'Alembert, which is the retarded potential, and then this gives me a solution which is valid, to this approximation. I have the nonlinear terms, okay? From this thing, already in 1916, actually, Drost computed the motion of planets, including the first nonlinear terms. And later, with Lorentz, he showed that you can extract from it a Lagrangian description. And already in 1917, they computed the Lagrangian at the first correction beyond Newton. So this Lagrangian is made of three parts. There is the Lagrangian for free test particles in Minkowski spacetime, so square root of 1 minus v squared. But that you can expand in v over c. Okay. So it gives the minus m squared, the kinetic term of Newton, and then the first corrections, 1 over 8 v squared reciprocal. There is a term that I will describe later, which is due to the one graviton exchange, and then there is a term which is nonlinear. Okay. It was just, so this was just a summary of what was known long ago for the motion of test particles. Sorry.
Just a minor question. I wonder why it's always credited to Infeld-Hoffmann.
I said Lorentz-Drost, yeah.
Yeah, but you said, but usually most people...
No, but it's because the Lorentz-Drost paper was totally forgotten.
But the difference is that they worked at the level of equations of motion instead of Lagrangian. I mean, that's why people remember them more.
Okay, Lorentz-Drost wrote both the equation of motion and the Lagrangian.
Mm-hmm.
Einstein-Hoffmann gave the equations of motion, and Fichte-Holz in Russia was the first one to show how to write the Lagrangian for Einstein-Hoffmann, which was already in Landau-Lifshitz 1950-something. Yes. So, but at the time, they had forgotten Lorentz-Drost. Now, black holes. As I said, Schwarzschild in 1916 discovered the first exact solution, spherically symmetric, of Einstein solutions that was not evidently, which was interpreted as a point mass. And later, people realized, but it's much more than a point mass. This is a black hole. But actually, the set of lectures here will be to say, yes, but let's go back to the description of saying this is also a point mass in a certain sense. So it is true that in a sense, you can use point masses for black holes. But before this, let's look at this solution. So it is a space-time with a component G00, which is 1 minus 2 gm over c square r. Let's keep that in mind, because this part of the metric is essentially the part which expresses the gravitational attraction that a black hole exerts. If I have a test particle moving around a black hole, this term in the metric will express the fact that I have a mass with an attractive Newtonian potential. And this is the Newtonian potential, although it appears in a relativistic formula. Now, it took time to understand that what happens at the point where r is equal to this, so that I have 0 here and 1 over 0 infinity here, is a special structure of space-time with a one-way hypersurface. Light cannot escape from this region, but can escape from outside. So there is this complicated strong field structure around the black hole. And inside the black hole, the things are even more complicated because we don't know yet what type of... There is a singularity inside of the black hole, which most people think is a space-like singularity in the general case, but it's debated. But although, I mean, black holes are very complicated objects, finally. They have a strong field locally. They have this hypersurface. Inside, there is something terrible going on. There are evidently quantum effects going on there. It is marvelous that you can describe the motion of two of these objects without having to know what happens inside, you know. So what is the method which allows to discuss the motion of two strongly self-gravitating bodies, like black holes, which are really the strongest possible self-gravity, or neutron star? A neutron star is less strong gravity than a black hole. It does not create an horizon, but it is h mu nu is like 40%. You know, the deviation from flat space in a neutron star is not 100%, but 40%. It's still a strong field. The method is called match asymptotic expansion. And so it was, in a sense, Einstein Feldhoffmann were using that. Then it was developed in the 70s and the 80s. And the idea is, so we cannot use a uniform perturbation theory. We cannot say that we have a small deviation of flat space-time everywhere. But what we can say is that if I stay sufficiently far away from the two bodies, this is a space-time diagram of this strongly self-gravitating body. Like in this region or this region, in this coordinate chart, I can use perturbation theory because I'm far from the bodies. So I can say I have Minkowski plus first order perturbation plus second order. But now, what perturbation theory can I use if I am near the body? I cannot use perturbation theory, but I can do a new perturbation theory, which is to say near each body, I can say that the metric here is the metric of an isolated neutron star because the companion is far away. So if I take the companion to infinity, I will have the metric of an isolated neutron star. And now I add perturbation, which are perturbation due to the existence of the companion. So it's a different perturbation theory. And the point is then you want to match the two things. You want to combine these two expansions to get information about the motion of two neutron stars or two black holes. Let me very briefly, as this is a course, describe how it is done. To do that, I need to set up the perturbation theory of, let's say, in the simplest case, a spherically symmetric neutron star. So I have a background metric which is spherically symmetric. And now I look at perturbation of this metric, of this body creating this metric, by a faraway companion. So I look at, let's move, I look at the perturbation of Einstein equation not around Minkowski spacetime, but around a non-perturbative solution, which is like a neutron star or a black hole. So you perturb Einstein equations. You use a technique first introduced by Ray J. Wheeler and Zerilli, where you use the spherical symmetry in the non-spinning case of the object to decompose in spherical harmonics, except that these are tensorial perturbations, so you need tensorial spherical harmonics. And then you write the fact that you need the background space-time described by two arbitrary functions, the stress energy tensor of the matter of the neutron star is described by a perfect fluid. Then you do perturbation. And after technology, you find that the perturbations satisfy a coupled system of equations that you can uncouple by combining equations. You can finally find that some of the functions describing the perturbed spacetime metric satisfy a simple radial equation of this type when you look at quasi-static perturbation. And then you can solve, so this thing is the analog of what is the perturbed gravitational potential around a spherical object. And as we know, the general solution in Newtonian theory of what would be the solution of Laplace equation decomposed in spherical harmonics would be to say I have two solutions. The one which goes like 1 over r to the L plus 1, which is something decaying at infinity, or the one growing that r to the power L, which are homogeneous solution of the Laplace equation when I multiply by YLM. And here you have the same thing, except you are in a black hole background, or so you find that this thing, which for L equal 2, so here I look at the quadruple deformation, which is the first one that enters. This thing grows like r squared, so this is the analog of a tidal deformation from coming from an outside bodies. You know, if I have the moon is exerting a gravitational field on the Earth. If I decompose this gravitational field, it will have something which goes like r squared, xi, xj times a tidal quadrupole moment. But I have another term in general, which is something which, when you look at it, decreases like 1 over r cubed, which would be if, for instance, the moon is deforming the Earth, and the Earth acquires a tidally induced quadrupole moment. It changes the shape of the Earth. And this quadrupole moment creates a gravitational field outside, which decreases like 1 over r cubed. You have the same thing for neutron star, and they are expressed by this quantity, which is called a love number. because of Oliver Love. No, I forgot his first name, Mr. Love, which expresses what is the tidal deformation, the tidal quadrupole induced by an external tidal effect on a fluid body, let us say. But you find that, yes, so two things. At the time, I had looked at that to argue that the only difference that you'll have between a neutron star and a black hole, because you want to know, when you look in the field outside, what is the influence of the fact that I had an extended body, okay? Can I see from the interaction of two bodies that I had neutron stars and not black holes, for instance, okay, or some more compact object? All this is encoded in this coefficient. And when you look at it, you find that this coefficient, at the end, in the equations of motion, creates something at the fifth post-Newtonian order, 5 loop, which is beyond what we can compute today. So this was the proof, what I call the effacing principle, that the fact that the object is, you know, as a black hole or a neutron star will not influence the thing outside up to a very high level of approximation. There was also the consequence that for a black hole, you need this coefficient to be 0, okay? So so finally, the tidal, the quadrupole effect in a black hole induced by external tidal fields for black hole is 0. While for a neutron star, you have a love number which is not 0. So we'll come back to this later. So at the end, so here I was saying, by doing this type of reasoning, you have information about the structure of the metric near each body and how it is deformed by the effect of the companion. Then you want to transform this information, to translate it in information about the motion of these two objects described by skeletons, described by point masses. Now, I have an extended object, which maybe is a black hole. I fictitiously say, no, now I work in the external coordinate system. I paint two world lines, which would be point masses that do not exist because really I have extended objects. And now I say, when I solve this problem without having the information about the inner body, do I have enough information from the previous reasoning to get the unique solution? And this is what I had shown at the time, that you can use the information if you look at the skeletonized description of gravitating bodies. So now I look at this formal problem. I take formally point masses. So I take the Einstein-Hilbert action. I add to it the action for point masses. So this is the geodesic action of a point mass moving in an external space-time. But I take it as an exact solution of Einstein's equation, which means that I will have infinities, you know, because this thing is the metric of space-time created by the body and its companion. So on the location of the body, this is infinite, actually, when I do imperturbation theory. So I will have the technical problem of renormalizing this, regularizing this, and showing that the solution is the one given by the correct method of match asymptotic expansion, which I've shown to some order. The basic idea is the following. Evidently, it is point masses, black holes are not point masses, okay? But a simple exercise is that if you take a point mass and you solve Einstein equation by successive perturbation theory, 1 over r, 1 over, you look for solutions with a point mass, you discard infinite self-fields and you solve it. What you find is you find this thing expanded in powers of g. So you check, which is what Schwarzschild had found actually, that a point mass generates a metric expanded in powers of g, but if you resum this metric, you get really a black hole. So this is in this sense that although point masses, black holes are not point masses, if you use point masses, you do get finally, by this effacing principle, the gravity of black holes. And now,
what about neutron stars?
Same thing. Up to 5 pn, the same thing gives neutron stars. And then when we will need to add the tidal deformation of neutron stars, we will add a term, which is the log number of neutron stars. When you do that, you find that you can express things in terms of diagrams. So let me re-explain what I said before. First, if you don't want, so let me say again that when you use the post-Newtonian approximation, you have the problem that you are always assuming that you know, that d0 of the metric, which means 1 over c d by dt of the metric, is much smaller than a space derivative di of the metric. So, this is true in the near zone, in the middle between the two objects, but it becomes wrong in the wave zone. So when you do that, this is very good for computing the interaction of two bodies because most of the interaction is in between, okay? But it will become wrong outside of the system. So it will generate some technical problems. That's why at the time, one had set up the post-Minkowskian approximation where you solve. So these are explicit form of Einstein's equation decomposed in powers of h alpha beta. There is the term quadratic here, explicit. So this is the cubic vertex of Einstein equation, you know, explicitly written. And then you can solve it explicitly. But already at the simplest case, which is one loop, the solution, you know, is complicated. And to compute it, you needed to compute a non-trivial integral, which was the one I was showing. This one, you know, is it's really a one-loop integral with a non-trivial integral over the intermediate point. And you needed already some technology to compute it, classically. That's why there is actually a complicated function that I did not write here, which comes log and things like that. Yes, and then from it you can compute the equations of motion of two bodies without making a small velocity assumption. But then in these equations of motion, at the time we also said, let's do, after you have got the equations of motion which included retarded effects, let's make a small velocity assumption. And the reason you can do it is when you have an interaction between two world lines, the time delay due to the exchange between this and this at this order of approximation is small. It is small compared to the orbital period. So you can use the so-called Lagrange expansion formula to take into account that a function of something which is retarded can be expanded to all orders in V over C, and you keep. So this was at the time the computation of the equations of motion up to V5 over C5. And in it, what was shown is that all the terms here, which starts with Newton's 1 over r square law, the Einstein-Infeld correction, the second order correction, which was first computed at the time, was conservative. That is, all that depended was coming from a Lagrangian. And by the way, there was already the subtlety that there was an error in Landau-Lifshitz at the time for this, even for electromagnetism, that actually there does not exist an ordinary Lagrangian function of Q and Q dot. The Lagrangian depends on Q, Q dot, and Q double dot, okay? So in these coordinates. But there exists still a Lagrangian description and a Hamiltonian description. And then you have an extra term. So the system is conservative. So the interaction of two bodies is conservative, derives from a Poincaré invariant Lagrangian up to order V4 over C4. And the first term which violates the existence of a Lagrangian is at V5 over C5. And it comes from the retarded interaction between the two bodies. As I already said, this technique, which is in principle nice conceptually because it does not make a near zone approximation, is not very good. I mean, it's more complicated if you want to extend it to higher orders. So to higher orders, it is useful to separate the question of what is the dynamics of two black holes in two parts. What is the conservative dynamics, neglecting radiation damping, starting at V5 over C5, and adding the radiation damping as an extra term computed from the emission of gravitational waves at infinity, okay? And for this thing, you can introduce the idea which was first introduced in electromagnetism by Fokker in 1929. Let me re-explain what I said. So we have an action which a priori is the action for the coupled dynamics of two point masses, which means, you know, in space-time I have two world lines, and then I have the field h mu nu, and the world lines with their position. So it's a coupled dynamics. The world lines create the fields, but also I could have an incident field. And what you can do, you are interested in the dynamics where the field acting is the one created entirely by the two world lines, that you don't have an incident gravitational field. And in this approximation, I mean, in this case, what you can do is to define the conservative dynamics by saying that the green function, which will be the interaction between the two world lines, is the time-symmetric Green's function. It was shown long ago by Fokker that if you want a conservative system, evidently you cannot allow the system to lose energy at infinity. Therefore, you must have, yes?
Is it possible to understand in simple terms why expansion involves both powers of V?
Why, sorry?
Why expansion involves all powers of V, not only even powers of V? Because normally in field theory, when you're doing expansion such small parameters, you're expecting to have an analyticity in the parameters of expansion.
Yes, so here the simple understanding is V over C here is it's a velocity. So if I change time in minus time, it means changes past and future. Now in the dynamics, if you have effects which are linked to radiation damping, which are linked to the dissymmetry, if you take boundary condition where the system emits at infinity, so the V5 over C5 is because I'm using retarded gravitational field. When you use time symmetric, yeah, good, thank you for the question. When you use formally time symmetric Green's function, all the terms odd will disappear, and you will have only even powers of V over C, and that will be invariant under time reversal and conservative. This is precisely what we talk about. So what I was saying is you start from an action which describes the coupled dynamics of the world line and the metric H, and Fokker had shown that it is enough to, although in general it is wrong in Lagrangians, in action, to replace a part of the dynamics by a solution of something, okay? But in that case, it is correct, that is to say, if you solve H as a functional of the world line, so H now is created by the world line, so at lowest order, this is saying that H mu nu is the Green function for the propagation of graviton times the source T mu nu. At next order, you will have these nonlinear terms with the cubic vertex of Einstein equation. And then if I insert this solution in the action, I will correctly get the action for the world lines, where I have integrated out the gravitational field. So let me insist, these things are an effective action. So it's a functional of two world lines, which is a sum of terms. One term is the one graviton exchange. This is a one loop effect, classical. Everything is classical. Each of these wiggly lines means the Green's function, the propagator of gravity. Each of the vertices means Einstein nonlinearities in Einstein action. Yes?
Sorry again.
Please, no.
In principle, there's those amplitudes that have imaginary part.
Not here, yes.
Why?
Because this is a classical problem, and for the classical problem, the time symmetric, okay, the Feynman Green function is actually modulo and overall I, the time symmetric thing, plus I, its imaginary part. So it's true that if you compute a quantum amplitude, you would have the I, but classically, it's not an approximation. You must use the real part of the Feynman propagator. You prove, and we have reproven it with Esposito Fares, that this gives the correct conservative dynamics under time symmetric interaction of two things. Okay. The precise link with the Feynman thing
So
is...
in this formula, G is not the...
No, sorry, yeah, there were two G's. Yeah, G was the Green function here, this G. Not Newton's constant. Let me also mention that there is an alternative, so this is the reduced action. Okay, there is an alternative way of computing the action, which has been emphasized by Goldberger and Rothstein, which initially I thought, but it's the same thing. So actually, I was convinced that their perturbation theory was exactly the same as the one we had been using for years. Actually, I discovered recently that there is a subtle difference, which is that instead of saying, you take the action for the field and the particles and you replace the field as a functional of the particles, you would say in a quantum type language that you are talking about, actually it would be in a sense W of J, given external sources, you compute the log of the formal functional integral, where I integrate over the gravitational field given external world lines as given sources, okay? But when you do that, So you compute this functional integral. Actually, you compute it by expanding everything and using Wick theorem. But when you use Wick theorem, you find that actually these are not exactly term by term the same thing. That it's a different way of computing the same thing. It's the same object, but slightly different, okay? It's just a minor detail. Okay, to be concrete, let me show you explicitly how it works at the one particle exchange, okay? Because this idea of Fokker action is not so well known usually. So, for instance, if I have electromagnetism, I have point particles moving in space-time. They are charged with such charge E coupled to the Maxwell field, EA. So this is the word line integration of mu on the word line. I have Maxwell action. I need to add a gauge fixing term in order to solve Einstein action, for instance, with the Lorentz gauge condition that I had. Now I can solve for mu as a function of the word line and put back in the action. It's a very simple calculation. What you find is the reduced action is the integral over the word line of the kinetic term, and what you recognize as directly the one photon exchange, where here you have an integral over the two word lines, and in between you have this one-dimensional green function of the interval between the 2 points. Okay? So this is a one-dimensional delta function, and this is the squared interval between the two word lines, 2 points, and you prove that this is the symmetric Green's function for Maxwell's equation. This thing satisfies D'Alembert of G equal minus 4 pi delta, and it comes in this way. The fact that this is a delta function simplifies things because you can compute it. Actually, the fact that this is a delta function means that this object is the sum of a retarded propagator delta t minus r over r and an advanced propagator. You see, we are explicitly time symmetric. Here there is r over c, so if I take the sum of the two, I'm symmetric now if under v square over c square, to all orders. And this satisfies it. If you do the same thing for gravity,
this is what was done by Wheeler and Feynman?
For 20 years later, yes. Yes. And what is interesting also is that if you look at they cite Fokker, okay? If you look at the paper of Fokker, actually, there are diagrams. There are diagrams of this type. And it is clear mentally that Feynman invented these diagrams because Fokker classically had introduced such diagrams. So the fact that now in classical gravity we are saying, okay, these are diagrams, actually goes back to 1929, you know. But Feynman added, except that Feynman had to find the Feynman Green's function. He was doing something else, okay? But he was inspired by the fact that classically you have these things. Now, if you do the same thing in gravity, you do the same thing, but here you have the linearized interaction with gravity. You have the linearized Einstein kinetic terms. It is easy to solve it at the one graviton exchange. What is the difference with electromagnetism? In electromagnetism, the source along the word line is a vector. We are talking about spin 1, so I have J mu, okay? In Einstein gravity, I have T mu nu, block inverse T mu nu, with the famous minus 1/2 of Einstein propagator. And if you write it explicitly, instead of this integral, it gives this integral, where I have a double integration over two lines. I have u mu u nu, which is the 4 velocity of this, 1 over d minus 2, and the same propagator. Just to show that at the one graviton exchange, things are trivial, okay? You can write them in 1 minute. If you want to go to one loop, you can do it keeping, Minkowski invariance, okay? Manifest Minkowski invariance. But when you want to go beyond, it gets really complicated because of the two-loop Einstein vertices and things like that. And this is where most of the computations, the ones that went up to 4 loop, these are 4 loops reduced by a post-Newtonian approximation, which actually simplify the vertices enormously. I will describe this, okay? So what you do is, formally, each time you have a propagator inverse block, inverse D'Alembert, which is inverse of Laplace minus 1 over c square over c square, you expand it as inverse Laplace, And you keep, this is your question, only even powers. Now you put technically the fact that you don't take the retarded propagator, but only time-symmetric propagator. And then you can do computations, okay? First, I have written before that I know the exact answer here. So it is an easy calculation to take this exact post-Minkowskian answer and expand it in V over C to get this term, okay? After this is, for instance, described essentially in Landau-Lifshitz, 1941. Now let's discuss more precisely what happens when I compute really some cubic vertices, okay? Which would be something difficult a priori because of Einstein vertices. But, so what should I do? In principle, I should start from Einstein action coupled to two word lines coupled to G mu. This is an explicit form of Einstein action. By the way, you know historically that Einstein was working with an action which is, okay, the so-called Einstein-Hilbert action is the, for good reason, is the integral over space-time in d dimension over 16 pi g of the curvature scalar as a functional of g mu nu, okay? The curvature scalar contains terms. The curvature scalar is of the type d gamma plus gamma gamma, where I remind you that gamma, the Christoffel symbols, are the first derivative of the metric with inverse of the metric, okay? So in this action, you have terms which are quadratic in first derivatives and terms linear in second derivatives. So it's an action with higher derivatives. What Einstein did at the time was to say, let's integrate by parts this term to get an action which is like the usual kinetic term, quadratic in derivatives. This is called the Einstein action. When you do that, you just get the gamma gamma, okay? You just have an explicit action. You need, so now this is quadratic in the gradients of the metric, okay? You need to put a gauge fixing terms because otherwise the propagator of Einstein equation is singular. You cannot solve Einstein equations. If you use harmonic coordinates, which means that this quantity is 0, you find that the gauge fixing term you need to put is quadratic in this and just with a coefficient minus 1/2, okay? You can rewrite it in terms of the so-called Gothic metric too. Let me also mention that recently the calculation done in the so-called IPhT approach, I've used this temporal Kaluza-Klein decomposition, which, as I said, was both linked to a good approximation to what were used before in ordinary calculation, but here it's done more systematically. So if you do it exactly, you parameterize the metric by exponential of a scalar and then a vector and then a tensor. Then you insert this in Einstein action and then you get something related. So why am I describing this? I'm describing this to give you an idea of how you really do the one loop computation in this thing. So what does it mean really for the motion of these things to compute these diagrams when you are in a post-Newtonian thing? When you are in a post-Newtonian thing, you need to compute these cubic vertices, and this term, for instance, means a term that will, there will be a potential generated by the second word line multiplied by a potential generated by the second word line. They combine non-linearly, and then this generates a potential acting on the first word line. Why this term means something where the first word line is generating a potential on the location of the second word line. What it means in terms of writing things and computing the effective action means that this type of terms, when you simplify them by the post-Newtonian expansion, these are terms, we are talking about terms which are cubic in h mu nu, okay? So remember, the action starts like dh square, and then there is h, dh, dh. Einstein action starts with terms evidently quadratic in the gradient of the metric, and then you have terms which are cubic, the cubic vertices of Einstein equation. Except that, you know, in general, here I have many indices. And I have many possible contractions. This is the difficulty of the Einstein vertex, is that you have about 20 different contractions of the various indices in general, okay? But if you are in a post-Newtonian approximation, all those things simplify enormously. First, because among the derivative acting on this, if I have a zero derivative, I can neglect it because it is smaller. So I only take space derivative, so it simplifies the thing. And among these indices, I know that I have H00, which is there, and that Hij is H00 delta Ij, so that all the other terms, I can replace them by one function, H00, which is the linearized perturbation in the time-time component of the metric, which is essentially the potential V that I had introduced before. I have said that if you write G00 as minus exponential minus 2V, this object satisfies a linear equation, D'Alembert V equal minus 4 pi times G sigma, where G now is Newton's G. And this is only this object that will come in all those complicated things. So because of this big simplicity of the post-Newtonian expansion, all those complicated terms, you know, they are cubic in the potential, but the cubic terms are V, special derivative of V, special derivative of V contracted. This term, when you look at it, there will be V square, Laplace of V, okay? Laplace of V means it's a delta function. It is something in this approximation. D'Alembert of V is sigma, is a source term also. But now I can just integrate by parts, you know. This term is the square of a gradient, but I can integrate by parts, and then you find easily that this term is equal to this term. And this term, actually, I can replace Laplace of V by sigma, which is a delta function of the two word lines, which means that this thing I can integrate without integrating. It is just the sum of V square term. And this is the way, this is why already in 1916, I mean, Drost could compute things to what we would call one loop order in post-Newtonian sense, because this complicated one loop thing is equivalent to something nonlinear. I mean, it is quadratic in Newton's constant, so it is indeed a sum of this term, but it is essentially the sum of the square of the potential of each body. Yes. Now, here I was describing the traditional way of computing things by solving Einstein equation, let's say in harmonic coordinates. A method, a very efficient method, has been to use the Hamiltonian formalism of Arnovitt, Deser, and Misner. This was first emphasized by a Japanese group. And then in Europe, Gerhard Schaefer was the one to realize that it might be efficient to go to higher order. So in that thing, what you do is you parameterize the Einstein metric in a different way. You have the metric of the, I said, this is a slicing of space-time. So you cut space-time in slices. You have an Hamiltonian evolution, okay? On each slice, you have a metric of space, gamma ij, and then you have functions that say how these slices evolve in space-time, which are called the lapse and the shift, which are essentially G00 and G0i. And what is surprising in this method, which looks very different than the usual one. In the usual one, you know, you think that the main potential, the main function which expresses the gravitational potential attraction is in G00, because this is where you see the Newtonian potential. But in the ADM formalism, G00 is a gauge function. It is like if you do, you know, for electromagnetism, you say that A0, the zero component, is actually, has no kinetic terms. And therefore, I can eliminate it and go to a Coulomb gauge where all the interaction will be in AI, transverse. You do the same thing here. You eliminate, really, G00 and G0i, and everything is put in a Coulomb type gauge for the gamma ij. So this means at the end that you get an Hamiltonian description where you have the metric gamma ij and its conjugate momentum pi. You have the position of the particles and their conjugate momentum p. And the Hamiltonian is an integral with Lagrange multiplier. Yeah, let me say it more precisely. When I said that G00 and G0I, which is lapse and shift, are eliminated. The basic reason is when you write Einstein action in this language, you find that the Einstein-Hilbert action is linear, contains, there are no time derivative of n and ni. They appear algebraically, which means they are Lagrange multipliers, which means that you have constraints, which are first-class constraints, which is the Euler Lagrange variation of n gives h equals 0 and hi equals 0. So after you do that, if you solve this constraint, so it gives elliptic equations. So Einstein equation now becomes a set of two constraints, the Hamiltonian constraints, which is linked to the energy, and the momentum constraint, which contain the momentum of the particles, as you can see. These are essentially elliptic equations that you can solve by solving Laplace-type Green's function perturbatively. And evidently, if you solve h and hi equals 0, it looks like the Hamiltonian is 0 now, okay? Because these are, I was linear in the Lagrange multiplier. But there is a surface term, and then actually the action is entirely due to the surface term that you can compute from the solution of these elliptic equations. You have part of the dynamics linked to gamma ij, which is still hyperbolic. That is, now you see the gravitational field is reduced to its gravitational wave part, the transverse traceless degrees. They are the 2 degrees of freedom of gravity are in gamma ij. The rest you solve as constraints. So it looks very different. All the calculations were done in the 2 different computations and were shown later to agree for gauge invariant quantities. Let me just describe technically when you compute. Yes, initially I said the thing you have to compute are given 2 word lines. What is the effective action due to the exchange of gravitons and nonlinear gravitons between the 2 word lines? But when you do it in a post-Newtonian sense, you replace the retarded propagator, block -1, by Laplace -1, which is an instantaneous propagator, plus corrections that you must take into account, evidently. But these corrections are still contain Laplace. So it is an expansion under instantaneous interactions, and we will see at which level it breaks down, which means that finally, when you look at the 2 word lines, they interact at the same time. So at the end, instead of having space-time integral, you have space integral. The real integrals that are done in PN are integrals where the 2 points now are points in space, and in between you have only instantaneous propagator. For the scalar part of gravity, you have like Laplace -1, and this is the transverse traceless, so you have here a non-trivial Einstein-type propagator for the spin-2 field, but still instantaneous. And now you need to compute this. Some of the most complicated integrals at you really have 4 loop integrals, okay? Like this one. Let me now mention very quickly, as this is a course, why dimensional regularization is essential in this thing. So first, let me describe analytic continuation. When you do this computation, you have integrals of the following type. For instance, you have something which contains, if I have 1 particle, it creates, maybe it is on the next thing, yes, analytic continuation. We have integrals which are divergent. Integrals over space, which are divergent near the point masses. How do you deal with that? We are going to deal by analytic continuation, which means that we will deform these integrals by changing some of the powers which are divergent by something which is a complex number. And then you consider integrals which are now f of x, which may be, a divergent integral. F of x dx would be infinite. You multiply by x to the b, where b is a complex number. So the basic idea is that this integral becomes well-defined as a meromorphic function of b if you take the real part of b large enough. Because if I have any power law divergence, like 1 over r to the 4, if I multiply by r to the b, where b real part is large enough, it becomes convergent, okay? Then you can compute the integral in the part where it exists. You prove that you can analytically continue it, And at the end, you want to continue down to the point where it was divergent. Now, the beauty of what happens in gravity is the result will be finite. We won't need really to have to renormalize things. Let me describe explicitly an example. If I have a Newtonian potential created in 3 dimensions by a point mass, this is a potential which is Gm over r, okay? If I compute this term, which is the gravitational energy of this Gm over r integrated over space, the gradient of 1 over r is 1 over r square. When I take the square, it's 1 over r4. I integrate over space. It's dr over r square. It is infinite. Evidently, this is saying that the energy of a point mass in the field around it is infinite. This is clear. If you do this calculation in d dimension, where now small d is the space dimension, the 1 over r becomes 1 over r d minus 2, where d is the space dimension. This integral becomes this integral. And now this integral, if I take the real part of d large enough, is well defined and actually is 0. So this is, I mean, Damour is just efficient to discard power law divergences. But evidently, as I said before, you have to justify this, and match asymptotic expansion justify this. Let me also quickly say that all the integrals that have been done by our groups were done in X space. Like the EFT people like in general to do computation in K space, in Fourier space, because you have integrals, okay? So these integrals can be represented with point masses. They can be either done really as space integral, or you do the Fourier transform of everything, and you have integrals over momentum space, okay? Here on this transparency, I have put all the formulas that allow to do for-loop computations, okay? So actually, it is remarkable that you can do for-loop computation with not so complicated formula, but I want to say technically what this is. At 2-loop, it was enough to use this formula due to Marcel-Ries, which is, if I have 2 point masses, this formula says the following. If I have 2 point masses, I take the distance between these 2 point masses and a point in space x. I raise these distances to arbitrary powers, a and b. I make the product of this, and I integrate over space, okay? This, as Marcel-Ries had shown, is equal to this modulo a product of 6 gamma function, okay? So it's a kind of easy computation, which is enough for 2 loops. But starting at 3 loops and 4 loops, one needs a more complicated integral because Vladimir Fock had found that there exists a nice formula, which is that if you want to solve a potential u, which is the solution of this thing, okay, when you solve Einstein equation at the cubic order, you have the potential of 2 bodies that interact non-linearly. So you have the product of the distance with derivatives, okay, because you have the derivative of this. And now you need to compute what is the potential generated by these nonlinear terms, okay? So you need to solve this thing. Actually, Fock had found that the solution of this is simply the log of R1 plus R2 plus the distance R12 between the 2 bodies, a very simple formula. Because of this simple formula, all the computations, after a while, they involve integrals with powers of R1, powers of R2, and powers of this combination. And Jaranowski and Schaefer have shown that this integral, which is more complicated now, can be computed explicitly in terms of beta function, incomplete beta function, which is an hypergeometric. So I want also to say that this thing has been computed in d dimensions. So you need some technology for these integrals. And what was amusing is that recently, Forfar, Mastrolia, Sturani, and Sturm, who have not yet been able to compute, far from that, the 4pm thing, but just a few static diagrams. To compute these static diagrams at 4 loops, which are really 4 loop integrals, you can reduce them to a master integral, which is this thing. So this, okay, is a Fourier space integral. It's what it is really what it shows, okay? Here I have scalar propagator 1 over k square. I have p coming out. You just put 1 over k square for each thing. You have the summation, okay? And then you ask, there are for loops. You want to compute this. In X space, it looks the same. And what was surprising is that this for loop integral had been computed in the literature, not analytically, but numerically, by using dimensional reduction, yes, from d to d minus 2, and computed with 500 digits. And then from the answer expanded in powers of epsilon, they could recognize that the analytical value of the finite term was pi square, okay? What is amusing is that in our paper with Jaranowski, we showed that actually you can compute this by elementary means. That is, somebody like a student in France at the baccalaureate level, maybe they don't know how to do integrals today, but something just with some logs, you can compute explicitly something which apparently was not computed by. So at the end, you get what I said before. So these computations have been done by 3 groups. One, let's say, around Germany and Poland, one around in France, and then the IPhT group, except that the IPhT group could not compute things at for loop. You get an explicit Hamiltonian, which starts with the Newtonian Hamiltonian, p square over c square, p4 over c4, p6 over c6, and p8 over c8. Let me, to finish this in the last minute, say that here, this is the Hamiltonian in the post-Newtonian sense at for loop. There is, all the terms here are algebraic. You cannot read them, but they are complicated polynomials, p to 12, things like that, 1 over r squared. But there is a term in this thing which is an integral. And the origin of this integral is, as we had understood in 1988, is I said that the problem of the post-Newtonian thing is that you are only valid in the near zone, okay? And evidently, you expect that at some level, there will be something wrong with saying that everything is instantaneous, because the interaction between 2 bodies really propagates. At some level, there should be an irreducible thing which is non-local in time. But this level is the for loop level, V8 over C8. And long ago, we had shown that at this level, there is a term in the interaction of 2 bodies. So when I have 2 word lines, there is a term in the interaction between the 2 bodies which cannot be approximated as being nearly instantaneous because it is really non-local in time. That it depends on the infinite past history, in the past and the future. And this term has appeared at 4 p.m. and gives, in a unique way, a non-local in time, but still time-symmetric contribution to the interaction of 2 bodies that appear explicitly at the for loop level. I think this is the end. Yes. Thank you for your attention.
Questions?
Can I ask again my question?
Yes, please.
Reformulated.
Yes.
This effective field theory for one body, if we come from another field, it looks at the same time looks a simple idea, like the idea of a self-consistent field theory. Usually it's not really exact, so there is some level of approximation.
Yes, here too.
Is it controlled, and why is it so successful? Could you just
yes, in a few words, because we will.
Yeah.
The main point, which in a sense I had shown on previous thing, is these formulas, which is the summary of what was done. They contain like about 120 terms. Okay, when you transcribe it in the effective one-body language, technically it becomes 7 or 8 terms. So you just replace a very complicated object by using actually canonical transformation in phase space. You use what really makes EOB, EOB works for several things. But one technical thing is that these very complicated things, by using Hamiltonian canonical transformations, most of the information is gauge here. And then you go, the effective metric in which the body is moving has only the gauge invariant content of this. That's the first thing, okay? Once you have done this, you have simplified so much this effective body metric that you can see how to go to merger. Because when you see this, merger is lost, you don't know what goes bad there. In the other description, you see precisely, and you can introduce a Padé resummation, which allows to describe when the two black holes merge. So indeed, there is nothing very sophisticated. You know, you simplify things, you go to the bare bones. It allows to see how to go to the merger, and it worked. Okay, we will rediscuss that later.
You mentioned several times that the IPhT people didn't go to 4 p.m. order. Do you think there is a technical reason, or just?
Yes, there are technical reasons that, contrary to the claims of many IPhT people, including Michel, it's not. It's not efficient.
Sector, the 4 p.m. is complete. It's the. It's
No. But we are talking here about the difficult part of the 4 p.m. What they say, it's more systematic. You have Feynman diagrams, you can write mathematical programs to computer. But at the end, you want to compute these things, okay? And when you do it in the Fokker type way, you do integration by parts all the time. While here now, so you have hundreds of diagrams, okay? And writing them explicitly does not help you to compute these things, okay? So it's the same calculation. Doing in K-space, I think, is not more efficient. I think we have proven that doing in X-space is more efficient. And just when you see, that's what I showed for the integral V. For instance, I had shown the one-loop computation. I had V square, V cube, you know, this thing. In X-space, it's trivial to compute it. If you do it in K-space, actually, it's less trivial. So I think there are several technical things. I should say that there are some conceptual clarifications in the IPhT thing. But from the technical point of view, I think the real thing, progress where they will be, is by using quantum amplitude method, where really now on-shell methods, double copy, are really simplifying things. You don't use Feynman diagrams, okay? You have something, and this, hopefully, that's the aim of describing here, would be very useful to improve the classical gravity part.
You were mentioning the
Somebody there.
No,
You meant somebody else?
Somebody else?
no, it's you. I'm sorry.
In the previous hour, you mentioned the EOB.
The what, sorry?
In the previous
Yes.
hour of the review,
Yes?
you mentioned that in the EOB, at the moment, 5 p.m., which is unknown, there was a piece from 5 p.m. which is unknown and is taken into account.
Yes?
And I just wonder how much does it make a difference for the agreement with the numerical relativity close to the actual merger?
I've looked recently at what would be the 4pn thing, and the 4pn is extremely close to numerical relativity already, but still, although we are talking, you know, close, not so close. Remember, in one of my slides, there were the two waveforms. The waveforms, they agree to 0.01 radians to merge. I mean, this level of accuracy, you need everything, you know, to be accurate to 10⁻3. You need extreme closeness.
So you say
we are not in the time where we're saying, okay, roughly the signal is like that. Now we want that the computed waveform agrees to such a small fraction of a radian that even in 20 years, when the signal-to-noise ratio will be much bigger, you know you are extremely close. So at this level, it is important to use numerical relativity. It is very important to use numerical relativity information.
Mm-hmm. And to go to higher orders in PN also analytical?
Actually, no. For the Hamiltonian part, now what limits the effectiveness of EOB is not the Hamiltonian part, but it is the radiation part, because I said there are two parts. You compute the conservative Hamiltonian, and then you resum the waveform. When you resum the waveform from the PN computation, if you don't do anything to this resummation, you just put all the logs, infinite number of leading logs, you find that you are very good up to the last orbit, but at merger, the waveform is incorrect by 10%. And then you use again numerical relativity to fit parameters in the waveform, and these are quite important, okay? And this is analytically very difficult. We use numerical relativity for this, okay? To have the agreement in energy loss at merger. At some level, the prediction would be good enough with the present data, but people want extremely accurate waveforms.
So, okay, thanks.